We're going to look at what's called the Pythagorean trig identities. You'll notice I've drawn in the coordinate plane again. There's our unit circle, and let's chuck a triangle in the first quadrant. Now it would be possible to find the coordinates of this point, which is going to be the length of the base here, and then the height would be the y value. We could work that out. We also know the equation of that circle. It's x squared plus y squared is 1. We know that to be true. Well, sine theta would be y over 1, so the y coordinate would be whatever sine theta is. And using a similar idea, we could say the x coordinate would be cosine theta. In fact, what we've just created are the parametric equations for a circle. So we've got it in terms of theta, would be the parameter. Okay. If I sub that into the equation of the circle, we get the first of our trig identities. And this is why it's called the Pythagorean trig identities, because when you think about it, the equation of the circle is actually Pythagoras' theorem applied to that triangle. X squared plus y squared is 1 squared. So sine squared plus cos squared, does not matter the size of the angle, will always equal 1. Now from there we can create the others. If I now divide everything by sine squared theta, well, sine squared over sine squared becomes 1, cos squared over sine squared would be cotan squared, and 1 over sine squared, well, the reciprocal of sine squared is cosec squared. There's the second of the trig identities. If instead I divide it by cos squared, well, sine squared over cos squared becomes tan squared, cos squared over cos squared, that's 1, reciprocal of cos is sec squared. So actually there's only one trig identity. It's just they're rearranged. So 3 different ones we tend to remember. Sine squared plus cos squared is 1, 1 plus tan squared is sec squared, and 1 plus cot squared is cosec squared. They are all actually the same identity, just written different ways. The other thing that's handy to remember, it's not a trig identity, but this relationship that tan theta is sine theta on cos theta. That can come in handy when doing these questions. So do some examples. We know that cos theta is 3/4, tan theta is negative, so what is sine theta? If I just draw a triangle, cos theta is 3/4. A bit of Pythagoras, I can work out the other side. Now I can read off this triangle and get sine theta, but I guess the question now is it positive or negative? They told me tan theta is negative, cos theta is positive. So therefore I must be in the 4th quadrant. And in the 4th quadrant, sine was negative. So the actual answer is negative √7 on 4. Simplify. Now I'm not suggesting that you would put all this working out down. In fact, I would love it if we looked at it and just bang, wrote the answer straight away. But just imagine you couldn't. So 1 minus cos squared, and you'd say to yourself, well, there's these 3 trig identities. And the nice thing about the trig identities is they all involve different ratios. So you can't use the wrong one. Cos squared comes from sine squared plus cos squared equals 1. So cos squared, if I rearranged it, I would get 1 minus sine squared. Play with that, I get sine squared. So 1 minus cos squared is sine squared. Sec squared minus tan squared. Oh, hang on. Now, not sure what it is. Well, I have a relationship. It's 1 plus tan squared is sec squared. So it kind of makes sense to substitute that in for sec squared. It's just 1. Tan theta, cos theta. Whoa, there's no squares there. So this is where I go, oh, well, I might use that relationship then. What happens if I do that? Tan is sine on cos. Oh, coses cancel. Sine theta, that's sine theta. Then we've got these things they ask us to prove. Prove that the left-hand side is always the same as the right-hand side. So I'll start with the left-hand side then. I want to play with this and try and get the right-hand side. So when I'm looking at something like this, I'm looking for trig squared, because I know that's the trig identity. In this case, I've got sec squared. So, right, well, 1 plus tan squared is sec squared, therefore I can substitute in 1 plus tan squared. Play around with that, see what we get. Well, the 2 minus 2 cancels. I have 2 tan squared on 4 tan. Excellent, we got some cancelling that will happen there. We get tan on 2. That's what we were looking for. Now when you are proving these trig identities, the approach I just took was I started with the left-hand side and I ended up proving the right-hand side. It would have been possible to start with the right-hand side and go and prove the left-hand side. That's certainly okay. And then there's a third option. I could work on both of them totally independently. But if I can show they equal the same thing, well, therefore they must have been equal if they're going to end up being the same thing. Never solve it like an equation. It is not an equation to solve because we don't know these things are equal. We're going to prove they're equal. I can only start moving things around once I know it to be a fact. If I know it's a fact, okay, I can manipulate it. But if I don't know it's a fact, I can't. That's what I'm trying to prove. So as I say, I could have started with the right-hand side. It's an unusual way of doing this question, I must admit. But if I saw that and go, well, okay, that's what I'm trying to do, I'm multiplying top and bottom by tan alpha so I can get the square into it. Tan squared, I could rewrite as sec squared minus 1. So I've got sec squared minus 1 on 2 tan alpha. Multiply top and bottom by 2, that was the left-hand side. So it certainly was possible to do it that way. Yet another strategy. Change what it is you're trying to prove. If I take everything to one side and say, I want to prove that's equal to 0, because sometimes that's easier to do. Show something is always equal to 0. If I can do that, if I can prove that, then I know that's a fact. Once I know it's a fact, I can move things around and get what I want. Okay, I want to prove that this is equal to 0. Algebraic fraction, so let's get a common denominator. The common denominator is 4 tan alpha. On top I get 2 sec squared minus 2 tan squared. But hang on a sec, sec squared is 1 plus tan squared. So now I have 2 plus 2 tan squared minus 2 tan squared. It's 0. I now know that's a fact. So that is true, therefore I can move the tan alpha on 2 to the other side, and that's the result that I want. So that's a strategy some people like to use. Okay, so we'll add 6F and 6G to our list of questions.